December 3, 1943. 7 miles south of the Rapido River, Italy. Staff Sergeant Thomas Burke watches his 4th Sherman tank of the morning sink into the Italian winter mud. The 30-ton M4A1, call sign Dakota Dream, lurches forward. Its Ford GAA V8 engine screams at full throttle. The tracks spin, throwing sheets of brown slurry into the air. The driver has the accelerator pressed to the floor. It doesn't matter. 30 tons of steel pressing down on 16-inch wide tracks. Ground pressure, 13 pounds per square inch. The mud cannot support that pressure. The Sherman sinks. The tracks lose purchase, digging trenches in the soft earth. The hull settles, belly armor making contact with the ground. The engine note changes to a higher-pitched scream as the transmission fights resistance it cannot overcome. Then the driver eases off. The engine drops to idle. The tank stops moving, immobilized. Stuck. Dead. Burke keys his radio. Tow cable. Baker 2-3. Needs recovery. Again. Recovery is tied up. Estimate 4 hours. Comes the response from Captain Holloway. 4 hours. If German artillery doesn't find them first. 300 yards behind him, 2 more Shermans sit motionless in the mud. Their crews stand beside them, waiting. The Wehrmacht doesn't wait. German 88mm guns in the hills have perfect fields of fire. Every immobilized Sherman is a stationary target. Burke has been in Italy for 47 days. He's a maintenance sergeant, not a tank commander, but he's learned more about how tanks die than most men learn in a year. This week, more American tanks are dying from mud than from German guns. He's 32 years old. Before the war, he worked as a welder in the Philadelphia Naval Shipyard. The Army recruiting sergeant saw Welder and assigned him to ordnance. Tank maintenance. The job keeps him alive, but it doesn't keep his tankers alive. That bothers him. The statistics are devastating. Between November 15th and December 5th, the 1st Armored Division reports 34 Sherman tanks immobilized due to terrain in the Mignano Gap sector. Not destroyed by enemy action, just stuck. Crews attempting recovery expose themselves to German fire for hours. 12 men killed, 23 wounded. Not in combat, in mud. The Italian winter is just beginning. Every week, more tanks get stuck. At current rates, by Christmas, the 1st Armored Division will have lost more combat power to immobilization than to enemy fire. The problem isn't unique to Italy. Field reports from North Africa, Louisiana training grounds, and Pacific Islands all describe the same limitation. The Sherman's tracks are too narrow. Standard VVSS, vertical volute spring suspension, uses 16-inch wide tracks. Ground pressure averages 13 pounds per square inch. On hard terrain, acceptable. On soft terrain, catastrophic. German tanks don't have this problem. The Panther, weighing 45 tons, uses 26-inch tracks. Ground pressure, 11 pounds per square inch. The Tiger, at 54 tons, uses 28-inch tracks. Ground pressure, just over 10 pounds per square inch. American tank crews watch in bitter frustration as German Panthers and Tigers cross muddy fields where their Shermans cannot follow. American engineers understand the principle. They know wider tracks equal better flotation. The problem is production. The Sherman was designed for mass production. Narrow tracks are easier to manufacture, lighter, fit on standard rail cars. Changing to wider tracks requires redesigning the entire suspension system. In 1941, nobody thought it mattered. They were wrong. The engineering solution exists. The Army Ordnance Department knows about the problem. HVSS, horizontal volute spring suspension, with 23-inch tracks, will solve it. Ground pressure drops to 9.5 pounds per square inch. Problem solved. Except, HVSS won't enter production until late 1944. First deliveries to Europe won't begin until December 1944. That's 12 months away. The Italian campaign cannot wait. Men are dying now. In October 1943, tank commanders requested wider tracks as an interim solution. The response was bureaucratically crushing. Track width modifications require extensive engineering analysis. Estimated timeline, 10 to 12 months. The same timeline as HVSS. No interim solution, only waiting. Translation: avoid mud. In Italy. In winter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. December 7th, 1943. Maintenance Depot, Caserta, Italy, 23 miles behind the front lines. Staff Sergeant Burke stands in a cavernous warehouse that once stored olive oil and wine for a local cooperative. Now it's filled with disabled Sherman tanks. The smell is diesel fuel, burnt metal, and damp earth. 18 tanks in various states of disrepair. Not one of them damaged by enemy fire. Every single one damaged by terrain. Tank number 30482219. Thrown track. The right track came off the drive sprocket while attempting to climb out of a drainage ditch. The crew spent 40 minutes under enemy observation trying to reinstall it. 2 men wounded by mortar fragments. Tank number 305142. Bent road wheels. The tank drove through mud so deep that debris packed between the wheels and the hull, bending the suspension arms. Total repair time, 16 hours. Tank number 308294. Broken final drive. The differential housing cracked under the stress of the tracks, trying to gain purchase in liquid mud. Transmission completely destroyed. Total loss. They'll cannibalize it for parts. Burke walks between these casualties, making notes on a faded clipboard. He's responsible for tracking repair timelines, parts requirements, and estimated return to service dates. It's tedious administrative work that he hates, but someone has to do it. Captain Holloway, the company commander, wants daily status reports. The battalion commander wants weekly summaries. Everyone up the chain of command wants to know when these tanks will be combat ready again. Burke's answer is always the same. As soon as parts arrive. As soon as we have time. As soon as we stop getting more damaged tanks faster than we can repair the ones we have. The Army operates on a replacement model. Tanks get damaged. Replacement tanks get shipped from the States. Damaged tanks get repaired and returned to service. In theory, the pipeline maintains adequate inventory. In practice, in Italy in December 1943, the pipeline is failing. Replacement tanks are arriving at a rate of approximately 12 per week for the entire Fifth Army. Tanks are being damaged at a rate of 28 per week. Do the math. The deficit grows daily. Within 2 months, at current rates, the Fifth Army will have 30% fewer operational tanks than authorized strength. That's not a logistics problem. That's an operational crisis. Burke is examining a broken track assembly, trying to determine if the links are salvageable or scrap, when he notices something he's looked at 1,000 times but never really seen. The end connectors. Each track link, each individual piece of the track, connects to the next link via a steel pin. The pin slides through holes in adjacent links. Then, an end connector, a wedge-shaped piece of hardened steel, slides over the pin and locks it in place. The end connector holds the entire track together. Without end connectors, the track is just a collection of individual links. With end connectors, it's a continuous belt capable of supporting 30 tons. Burke picks up one of the end connectors from the disassembled track, turns it over in his hand, feels the weight, examines the shape. Standard Army Ordnance Part Number 7055614. Hardened steel, 4 inches wide at the base. Tapers to 3 inches at the top, weighs approximately 1.5 pounds. There are 64 of these on each Sherman. 32 on the left track, 32 on the right track. 64 connection points where the track makes contact with the ground. And that's when the idea hits him. Not gradually, not through careful deliberation. Just suddenly, completely, the way good ideas sometimes arrive, fully formed. The problem with Sherman tracks isn't the track links themselves. The links are fine. Hardened steel, rubber pads on some models, excellent design. The problem is ground contact area. Specifically, there isn't enough of it. The track is 16 inches wide, but it's not solid. It's made of individual links, each 4 inches wide, connected by end connectors. Between each link, there's a gap. The actual ground contact happens at the rubber pads on the links and at the narrow end connectors. If you could increase the width of the end connectors, you'd increase the effective width of the entire track without changing anything else. Burke does the math in his head. 64 connectors per track, 128 total. Each connector is currently 4 inches wide. If you made each connector 8 inches wide, you'd effectively double the track width. Double the width equals half the ground pressure. Half the pressure equals twice the flotation. A Sherman with 8-inch wide end connectors would have ground pressure comparable to a Panther, maybe better. But can it work? Wider connectors mean more weight. More weight on the track means more stress on the suspension. Will the VVSS bogie wheels handle it? Burke walks over to one of the intact Shermans, climbs up onto the hull, lies down on his stomach, and stares at the suspension. The bogie wheels are mounted on vertical volute springs, heavy coil springs designed to absorb shock. They're rated for the weight of the tank, plus combat load, plus rough terrain. Adding a few £100 of wider end connectors shouldn't exceed the load limit. Probably. Maybe. He'd need to test it to be sure. And there's another problem. The end connectors lock onto track pins. The pins are standard diameter, 5/8 of an inch. If you make the connectors wider, you need to make sure they still fit properly on the pins. Too loose and they'll fall off. Too tight and they won't install. Burke measures a connector. The hole for the track pin is precisely machined. Any modification would have to maintain that precision. He spends the next hour sketching designs on a piece of scrap paper. Different shapes, different attachment methods. He considers welding extensions to the sides of existing connectors. Too weak. The weld would fail under stress. He considers machining entirely new connectors from plate steel. Too time-consuming. They'd never produce enough. Finally, he settles on the simplest approach. Weld a flat plate to the bottom of a standard connector. The plate extends outward on both sides, increasing the width. The connector itself remains unchanged. The pinhole remains standard. Installation remains identical to normal procedure. The only difference is the footprint. Burke finds a piece of scrap steel plate in the corner of the workshop. 1/4 inch thickness. Mild steel, not hardened, but it should be strong enough. The plate originally came from a destroyed German half-track. American forces strip every destroyed enemy vehicle for useful metal, waste nothing. Burke measures the plate, 12 inches wide. Perfect. He marks it with chalk, measuring carefully. 4 inches by 6 inches for each extension. He'll make 4 to start. Proof of concept. He clamps the plate in a heavy bench vise and fires up his oxyacetylene cutting torch. The torch hisses, the flame burning, blue-white at 3,000 degrees. Burke cuts slowly, precisely. The molten steel drips away, leaving a clean edge. 4 rectangles, 4 inches by 6 inches each. They're rough, edges slightly uneven, but that's acceptable. This is a prototype. Precision can come later. Next, he takes a standard end connector from the parts bin, part number 7055614. He positions one of the steel rectangles against the bottom of the connector. The rectangle extends 2 inches beyond the connector on each side. That'll increase the effective track width from 4 inches to 8 inches. Burke clamps everything together, double-checks the alignment, and strikes an arc with his welding electrode. The weld is crucial. Too weak, and it'll fail under load. Too strong, paradoxically, and it'll create stress concentrations that could crack the base metal. Burke learned this in the shipyard. Welding isn't just about joining metal. It's about understanding how forces transfer, through joints. He runs a continuous bead along each edge where the plate meets the connector. Slag spatters. The weld glows orange. Burke works methodically, maintaining consistent speed and heat. When he finishes, He lets the assembly cool, then chips away the slag and inspects the weld. It's ugly, rough, but it's solid. The plate is firmly attached to the connector. The result looks absurd. The extension sticks out from the connector like a flat foot, ungainly and crude. It's not elegant. It's not precision engineering. It's not what any design manual would recommend. But Burke doesn't care about aesthetics or design manuals. He cares about surface area. He's just doubled the width of one ground contact point from 4 inches to 8 inches. If this works on one connector, it'll work on 64 connectors. And if it works on 64 connectors, it'll work on every Sherman tank in Italy. Burke makes 3 more modified connectors, working through the evening. The sun sets, the workshop gets cold. He keeps welding. By 2200 hours, he has 4 completed prototypes, 4 ugly, crude, entirely unauthorized modifications to standard army equipment. He wraps them in a canvas tarp and heads to the maintenance company headquarters. Wider end connector. For mud. Did Ordnance approve this? No. Did anyone approve this? Technical Sergeant Raymond Mitchell picks up the modified part, examines the weld closely under the workshop light, runs his thumb along the joint, tests the strength by trying to flex the plate against the connector. It doesn't move. This is field modification of Army equipment without authorization. Yes, Sergeant. You know what happens if this fails. If we install these things on a tank and the welds break and the track comes apart in combat and somebody gets killed, that's on you. That's criminal negligence. Court-martial, Leavenworth. Dishonorable discharge. Yes, Sergeant. But what's happening now? Tanks getting stuck. Crews getting killed trying to recover them. That's happening every day. 3, 4, 5 times a week. I can't stop that by following regulations. The regulations say wait for HVSS. HVSS is a year away. How many more men die while we wait? Mitchell takes a long drag on his cigarette. Exhales slowly. Looks at Burke. Really looks at him. Sees a man who's past caring about his own career, who's decided that saving lives matters more than saving his stripes. Mitchell's been in the army for 15 years. He knows that look. It's the look of a man who's made his choice and won't be talked out of it. You really think this will work? I think it's worth testing. Worst case, it doesn't work and we scrap them and nobody needs to know we tried. Best case, we save some lives. Maybe a lot of lives. Best case, we save some lives. Mitchell repeats slowly. He stands up, walks over to the window, looks out at the darkness and the rain. 1943, 2 years of war. 2 years of watching men die. 2 years of filing reports about equipment losses. Maybe it's time to stop filing reports and start fixing problems. He turns back to Burke. How many can you make by tomorrow morning? Be specific. Burke does the math quickly in his head. Depends on how many welders I can get and how much scrap steel we have available. One man, working through the night, maybe 16 to 20 connectors. With help, maybe 64. Enough for one complete tank. With more help and more steel, maybe 128. Enough for 2 tanks. You'll have help, Mitchell says. He opens the door, steps out into the maintenance company area, and shouts into the darkness. De Luca, Kowalski, Hernandez, get your asses over here. Now. 3 men emerge from their tents and hurry over. Private Anthony De Luca, 19 years old, Chicago, Italian immigrant family, worked in his father's metal fabrication shop before the war. Private Eddie Kowalski, 22, Detroit, 3rd-generation Polish, worked at the Ford River Rouge plant welding automotive frames. Private Miguel Hernandez, 24, San Antonio, learned welding in the Civilian Conservation Corps building bridges in Texas. All 3 are qualified welders. All 3 are exactly what Burke needs. Mitchell addresses them formally. You 3 are assigned to Sergeant Burke for special duty, priority maintenance. You'll work through the night, no questions, no details shared outside this group. Report to the workshop immediately. The three privates glance at each other, confused but obedient. Yes, Sergeant. Mitchell turns back to Burke. You've got until 0600 hours. That's 7 hours. If you can make 64 by dawn, we'll install them on Lieutenant Hammond's tank and test them. If they work, we make more. If they fail, this conversation never happened, and you're solely responsible. Understood? Understood, Sergeant. That night, December 7th, into December 8th, 1943, 4 men work through the darkness in the maintenance depot workshop. Burke explains the modification to the 3 privates, showing them his prototype. DeLuca picks it up, examines the weld, immediately understands what Burke is trying to do. You're increasing ground contact area to reduce pressure. Like snowshoes. Exactly like snowshoes. Will it work? Only one way to find out. They set up an assembly line. Burke and Kowalski cut steel plates from salvaged German vehicle hulls. DeLuca and Hernandez weld the plates to standard end connectors. They work in shifts. 2 men cutting, 2 men welding, then switching to prevent fatigue errors. The workshop fills with the sound of cutting torches hissing, welding electrodes crackling, slag being chipped away. The smell is ozone and burnt metal and sweat. By 0200 hours, they've completed 32 connectors. Halfway there, Burke's arms ache from holding the cutting torch. Steady. Hernandez has welding flash burn on his forearms from sparks that got past his sleeves. Kowalski's hands are blistered from handling hot metal. None of them slow down. They keep working. By 0400 hours, 50 connectors done. They're running low on scrap steel. Burke sends Kowalski to scavenge more from the vehicle graveyard outside. Kowalski returns with sheet metal stripped from a destroyed German SDKFZ 251 half-track. Perfect thickness, perfect size. They keep cutting, keep welding. By 0545 hours, 64 modified connectors sit in a row on the workshop floor. Some are better than others. Some have prettier welds. Some are slightly different sizes. But all of them are functional. All of them will increase track width from 16 inches to somewhere between 20 and 22 inches. That's enough. That should be enough. Burke and his team are exhausted. None of them have slept. Their uniforms are covered in metal dust and welding splatter. DeLuca has a burn on his hand from picking up a connector before it cooled, but they're done. 64 modified end connectors, enough for 1 Sherman tank, enough to test the concept, enough to find out if a maintenance sergeant with no engineering degree can solve a problem that Army Ordnance says requires a year of development. December 8, 1943, 0630 hours. Mitchell arrives at the workshop as promised, inspects the connectors, says nothing. Then he nods. Get them installed. Hammond's tank, Rolling Thunder. I already told him his tank is getting modified tracks for a field test. He doesn't know what that means. Let's keep it that way until we know if this works. Installing 64 modified end connectors on a Sherman tank is not difficult, but it's time-consuming. Each connector must be installed in the proper sequence. Each one must be properly seated on the track pin. Each one must be tapped into place with a sledgehammer and have its wedge bolt tightened to specification. Burke and his team work methodically. Left track first, 32 connectors, then right track, 32 more. By 0900 hours, Rolling Thunder has a complete set of modified tracks. The tank looks strange. The connectors stick out from the sides like flat feet, making the tracks appear comically wide. Lieutenant Hammond walks around the tank, staring at the modifications. Sergeant Burke, what exactly did you do to my tank? Modified the end connectors for better flotation, sir. Wider footprint. Should improve mobility in soft terrain. Should? You don't know? This is the first test, sir. Hammond looks at Mitchell. Sergeant Mitchell, did Ordnance approve this? Mitchell meets his gaze steadily. Sir, this is a field expedient modification developed to address operational mobility limitations. It has not been submitted for formal approval because the approval process requires timeline incompatible with current operational requirements. Hammond passes that bureaucratic language and understands exactly what it means. No, Ordnance didn't approve this. Yes, we're doing it anyway. And if it fails, somebody's career ends, possibly several careers. He thinks about the 12 men from his division killed trying to recover stuck tanks in the past month. Thinks about the assault scheduled for December 15th. Thinks about how many more men will die if the tanks can't move. All right, we'll test it. Where? Burke points across the depot yard. That area, sir. The swamp. Standard Shermans avoid it. It's known as the tank killer. A Sherman got stuck there 2 weeks ago, sank up to the hull, took 4 hours and 3 recovery vehicles to extract. You want me to drive my tank into ground that's known for killing tanks? Yes, sir. If the modification works, you'll cross it. If it doesn't work, we'll pull you out and strip the modifications off and pretend this never happened. And, if the modifications fail catastrophically, if the track comes apart, then I go to Leavenworth, sir, and you get a new tank. Hammond looks at his crew. His driver, Corporal James Morrison. His gunner, Private First Class Robert Talley. His loader, Private Kenneth Walsh. His bow gunner, Private Carl Hendricks. All of them looking at him, waiting for the decision. They've been in combat for 6 weeks. They've seen tanks get stuck. They've seen crews die. If this modification gives them a better chance, they'll take it. Mount up, Hammond orders. Burke watches as Hammond's crew climbs into rolling thunder. Watches as Morrison starts the Ford GAA engine. The V8 roars to life, settling into its characteristic rumble. Morrison lets it warm up for 2 minutes, watching the gauges. Oil pressure good. Coolant temperature rising normally, everything nominal. He shifts into first gear. The tank lurches forward. The modified tracks clank against the drive sprockets, sounding slightly different than standard tracks, heavier, but they engage properly. The tank moves. Standard Shermans avoid the swamp. It's a 100-yard-long stretch of ground on the south side of the depot, a natural depression that collects rainwater and never fully dries out. The mud there is liquid, deep, treacherous. 2 weeks ago, an M4A3 tried to cross it and sank to the hull. The recovery operation took 4 hours, required 3 M32 tank recovery vehicles, and damaged the stuck tank's transmission so badly it had to be sent to Naples for depot-level repair. Since then, the swamp has been marked off limits. No tanks, no vehicles, too dangerous. Rolling thunder lines up on the edge of the swamp. Morrison revs the engine. The tank surges forward. The tracks make contact with the liquid mud. And something different happens. The tank doesn't sink. Or rather, it sinks slightly, maybe 3 inches, then stops. The wide-end connectors, spreading the tank's weight across a much larger surface area, prevent the catastrophic sinking that normally immobilizes Shermans in this kind of terrain. The ground pressure, reduced from 13 pounds per square inch to approximately 10 pounds per square inch, is low enough that the saturated ground can support it. Morrison accelerates. The tracks dig in slightly, find purchase, drive the tank forward. Rolling thunder crosses the swamp at 5 miles per hour. Not fast, but steady. No bogging, no track throwing. No transmission strain. The tank crosses 100 yards of ground that should have stopped it in 45 seconds, and emerges on solid ground on the far side without incident. Hammond opens his hatch, stands up in the turret, looks back at the swamp they just crossed. He can see the track marks in the mud, shallow, barely 3 inches deep. A standard Sherman would have sunk to the hull. His tank barely left a mark. He climbs out of the turret, walks back across the swamp on foot, his boots sinking 6 inches into the mud with every step. The ground that just supported a 30-ton tank can barely support a 180-pound man. The physics shouldn't work. But it does. The modification works. Hammond walks up to Burke. "Sergeant, what did you do to my tank?" "Modified the track connectors, sir. Wider footprint, better weight distribution. It worked. We just drove through ground that stops everything. We didn't even slow down." "Yes, sir. Can you do this to the rest of the company? The rest of the battalion?" Burke looks at Mitchell. Mitchell nods slowly. "We can do the whole battalion, sir," Burke says. "If nobody stops us, we'll need steel, we'll need time, we'll need welders. But yes, sir, we can do this." Hammond makes his decision. "Consider yourself authorized." "Not by me. I'm just a lieutenant. I can't authorize field modifications, but I'm requesting it, formally, in writing if necessary. My company needs this. The battalion needs this. Hell, the whole division needs this. How fast can you work?" "Assembly line production with adequate manpower and materials. Maybe 8 tanks per day. 48 tanks in a week. You've got 3 days until we jump off for the Mignano assault. How many can you do in 3 days?" 24 tanks. Maybe 30 if we work around the clock." "Then work around the clock. I'll get you the manpower. I'll get you the steel. I'll handle Mitchell's chain of command if anyone objects. You just keep building these things. My crews need to be able to move. You just gave us that. Don't stop." The next 72 hours, December 8th through December 11th, 1943, become a manufacturing operation conducted entirely outside official channels. Burke's maintenance team expands. Mitchell assigns every available welder in the battalion to the project, 12 men total. They work in 3 shifts, 8 hours each, around the clock. The workshop never stops. Day and night, the sound of cutting torches and welding arcs fills the depot. They develop an assembly line process. Station 1, cutting. 2 men with oxyacetylene torches cut steel plates from salvaged enemy vehicles. German half-tracks. Destroyed Italian trucks. Knocked out panzers. Any steel plate 1/4 inch thick or greater becomes raw material. Station 2, preparation. 2 men grind the cut edges smooth, remove any rust or paint, prepare the surfaces for welding. Station 3, welding. 4 men, working in pairs, weld the plates to standard end connectors. Each welder completes 1 connector every 8 minutes. Station 4, finishing. 2 men chip away slag, inspect the welds, test the joints for strength. Station 5, installation. 2 men install the finished connectors on tanks. The process is crude but efficient. They're not building precision equipment, they're building functional equipment. Pretty doesn't matter. Strong matters, working matters. Every 8 minutes, a new connector comes off the line. Every hour, 7 to 8 connectors. Every day, 160 to 190 connectors. Enough for 2.5 to 3 complete tanks. Mitchell handles the politics. When the battalion maintenance officer, Captain Thomas Greer, asks why the welders are working triple shifts, Mitchell shows him rolling thunder crossing the swamp. Greer watches, says nothing. Then he asks, "Did Ordnance approve this?" "No, sir." "Are you doing it anyway?" "Yes, sir." Greer thinks for a long moment. He's 34 years old, regular army, commissioned from West Point in 1933. He's seen enough combat to know when to follow regulations and when to ignore them. "I didn't see this. I don't know anything about it. If it works, we'll claim it was battlefield improvisation. If it fails, you take the blame. Understood?" "Understood, sir." "How many tanks can you modify before we jump off?" 24 to 30, sir, depending on steel supply. "There's a German vehicle graveyard 12 miles north, plenty of salvage. I'll send trucks." By December 11th, 42 Sherman tanks have been retrofitted with what everyone is now calling duckbills. The name comes from Private Kowalski, who looked at the wide, flat extensions and said they looked like duck feet. The name sticks. It's descriptive. It's memorable. It's easier than saying modified extended end connectors. The crews start painting little duck symbols on their turrets. Unofficial, unauthorized. Nobody cares. If the duckbills keep their tanks moving, they'll paint whatever they want. Nobody asked for authorization from 5th Army headquarters. Nobody filed paperwork with Army Ordnance. Nobody informed anyone above battalion level. They just built them and installed them because tanks were dying and men were dying, and waiting for official approval meant more death. Sometimes in war, you ask forgiveness instead of permission. Sometimes you don't even ask forgiveness. You just do what needs doing and hope the results justify the violation. December 15th, 1943, 05:30 hours. The Fifth Army launches its assault on German positions defending the Mignano Gap. This is the offensive that's supposed to break the German winter line and open the road to Rome. But first, American forces have to cross the most hostile terrain in Italy. The valley floor is a nightmare. 3 days of rain have turned it into a swamp. Visibility is poor, fog rolling in from the mountains. Temperature is just above freezing. German defensive positions sit on high ground, commanding observation of every approach. They have pre-registered artillery concentrations on every obvious avenue of advance. They've been preparing these defenses for weeks. They're ready. Standard military doctrine says armor cannot operate in these conditions. The ground is too soft. Tanks will bog down within minutes and become stationary targets. German anti-tank guns will destroy them systematically. The smart play is to wait for the ground to harden. Wait a week, wait 2 weeks, wait for drier weather. But Fifth Army doesn't have weeks. The Italian campaign is already behind schedule. Washington is demanding results. The British Eighth Army, fighting on the Adriatic coast, is making progress, and the Americans are expected to keep pace. So Fifth Army attacks, into the mud, into the fog, into the German guns. 1st Armoured Division attacks anyway. 42 Shermans with duckbill modifications form the spearhead of the assault. They advance in 3 columns, each column following a narrow dirt road that leads toward German positions. The plan is simple. The duckbill-equipped Shermans will cross the valley floor, where standard tanks cannot. Find routes through the mud, create paths for the following infantry. They're pathfinders. Scouts. Guinea pigs. If they get stuck, the entire offensive stalls. If they get through, the infantry can follow. Everything depends on whether Burke's crude welded modifications actually work in combat conditions. Lieutenant Hammond's platoon leads the center column. 5 Shermans, all with duckbills. Rolling Thunder in the lead. They roll out at 05:30 hours, engines rumbling in the pre-dawn darkness. The fog is thick enough to taste. Visibility, maybe 50 yards. Hammond, standing in his turret with his hatch open, can barely see the tank ahead of him. But he can feel the ground, soft, liquid. The kind of ground that ate tanks 3 weeks ago. Rolling Thunder's tracks bite into the mud. The tank sinks maybe 4 inches, then stops. The tracks maintain grip. The tank keeps moving. 5 miles per hour, not fast, but steady. No bogging, no loss of traction. The duckbills are working. Behind him, 4 more Shermans follow, their tracks churning through mud that should stop them. They don't stop. They keep moving. At 06:15 hours, German artillery opens fire. They've spotted the tank columns through the fog. 88mm guns, 105mm howitzers, Nebelwerfer rocket launchers. The valley floor erupts with explosions. Mud, shrapnel, and fire. Hammond's platoon accelerates, trying to get through the kill zone as quickly as possible. A standard Sherman platoon would be stuck, unable to maneuver, sitting ducks for the German guns. But Hammond's tanks keep moving. When explosions block the road, they drive around the craters, off-road, through ground that's even softer than the road. The duckbills let them maneuver where standard tracks would fail. Mobility equals survival. Rolling Thunder takes a near miss from an 88. The round hits 10 yards to the left, exploding in the mud. Shrapnel pings off the armor. Hammond feels the concussion through the hull. But the tank doesn't stop, doesn't get stuck. Morrison, the driver, keeps his foot on the accelerator. The tank surges forward, tracks digging through. Liquid mud, duckbills distributing weight across a wide enough area that the ground, barely, supports them. They cross another 100 yards, 200 yards, 300 yards. They're through the kill zone. They're still moving. By 0700 hours, 42 duckbill-equipped Shermans have crossed the valley floor. 3 have been hit by German fire. 1 destroyed, crew killed. 2 damaged but mobile. 39 are still operational and have reached the far side of the valley. Compare that to the follow-on force. 18 standard Shermans attempted to cross the same ground. 12 got stuck within the first 500 yards. The crews had to abandon them under fire. 6 made it across, following the tracks left by the duckbill Shermans. The difference in success rate is stark. Duckbills, 93% mobility. Standard tracks, 33% mobility. The modified tracks distribute weight across a wider surface area. Ground pressure drops from 13 pounds per square inch to approximately 10 pounds per square inch. That 3-pound difference, seemingly trivial, makes the difference between mobility and immobilization. It's the difference between life and death. The physics are undeniable. Wider tracks equal better flotation. Burke's crude, unauthorized field modification just proved a principle that Army Ordnance has been reluctant to acknowledge. Lieutenant Hammond's after-action report, filed December 16th, is terse and factual. Military documents always are. But between the bureaucratic language, the truth is clear. At 14:30 hours on 15 December, a platoon encountered saturated ground conditions approximately 6 inches deep, extending for 1,200 yards. Expected immobilization based on previous experience with standard track configuration. Tanks, equipped with modified extended end connectors, maintained mobility throughout transit. No mechanical failures, no immobilizations. Modified track. Extensions performed as designed. Ground pressure reduction sufficient to prevent catastrophic sinking in liquid mud. Recommend immediate adoption across all armoured units. Further recommend formal engineering review and mass production authorization. The German defenders noticed something wrong. Their defensive plan relied on terrain channeling American armor into predictable avenues of approach. The muddy valley floor was supposed to be impassable. Their intelligence reports, their reconnaissance, their defensive calculations all assumed that American tanks couldn't cross soft ground. They positioned anti-tank guns to cover the few hard surface roads. They planned to destroy American armor as it bottlenecked on those roads. But the Americans aren't staying on the roads. They're crossing the mud. They're appearing in places the Germans calculated were impossible. Defensive positions planned to exploit predictable American movements suddenly face armor, attacking from unexpected directions. The entire defensive scheme unravels. A captured German officer, Major Klaus Richter, 89th Infantry Division, interrogated on December 18th, expresses confusion and frustration. Your tanks crossed the river valley. That ground stops our Panthers. We observed it. We tested it. A Panther could not cross that ground without bogging down. How did you do this? We could not understand. Your tanks should not have been there. Your tanks were where our plans said they could not be. Our anti-tank positions were in the wrong places. You changed something. Your tanks are different. How? The interrogator, a captain from G2 Intelligence, doesn't have an answer. He doesn't know about the duckbills. Nobody above battalion level officially knows about the duckbills yet. The modification is spreading through word of mouth between maintenance crews, an unauthorized field expedient being replicated because it works. But it hasn't reached official channels. There's no memo, no directive, no technical bulletin. Just welders talking to other welders, maintenance sergeants sharing measurements. Tank crews requesting the modification because they've seen it work. And it keeps working. For 5 days, from December 15th through December 20th, the 1st Armoured Division grinds forward through the Mignano Gap. The duckbill-equipped tanks maintain mobility in conditions that should stop them. They cross muddy fields. They maneuver off-road. They reach firing positions that standard tanks cannot reach. The modification gives them a tactical advantage the Germans didn't anticipate and cannot counter. It's not a war-winning superweapon. It's just a simple fix that makes American tanks slightly more mobile. But in war, slight advantages compound. Mobility equals flexibility. Flexibility equals options. Options equal victory. December 20th, 1943. Major General Ernest Harmon, commanding the 1st Armoured Division, conducts an inspection of forward maintenance facilities. He notices that every Sherman in the motor pool has unusual track modifications. He stops a tank crew. "What's on your tracks?" "Duckbills, sir. The welders made them." "Ordnance approved this?" "Don't know, sir. We just know they work." "No, sir. I made them." "You modified Army equipment without authorization?" "Yes, sir." "Do they work?" "Yes, sir. We've had 0 track-related immobilizations on modified tanks in 8 days of operations, 12 immobilizations on unmodified tanks in the same period." Harmon picks up one of the modified connectors. "The weld is rough, ugly, exactly what you'd expect from field fabrication, but it's solid. The concept is sound." "Sergeant, how many of these can you produce?" "As many as you need, sir. We're using scrap steel and standard welding equipment. 8 minutes per connector, 64 per tank, about 8 hours per complete installation." Harmon makes a decision that will change armor tactics for the rest of the war. Instead of court-martialing Burke for unauthorized modifications, he orders immediate mass production. Every Sherman in 1st Armored Division will receive duckbill connectors. Furthermore, he sends a priority message to 5th Army Headquarters, describing the modification and recommending immediate theater-wide adoption. The response from higher command is bureaucratic resistance. Army Ordnance Department opposes field modifications without engineering approval. The connectors haven't been stress-tested. Metallurgical analysis hasn't been performed. Failure rates are unknown. The proper procedure is to submit the design to Aberdeen Proving Ground for evaluation, testing, and approval. That process takes 6 months, minimum. Harmon sends back a single-line response. "In 6 months, how many more tanks will be stuck in the mud?" January 1944. The modification spreads through unofficial channels. Maintenance sergeants talk to other maintenance sergeants. Welders share measurements and techniques. Small workshops across Italy begin fabricating their own versions of the duckbill connectors. Some use thicker steel, some make them slightly wider. Some improve the weld technique. All of them work. By late January, an estimated 200 Sherman tanks in Italy have been modified with extended end connectors. Not officially, not through supply channels, through improvisation. The modification improves mobility so dramatically that tank commanders actively seek out maintenance units capable of installing them. A British tank officer, observing American Shermans operating in muddy conditions near Cassino, writes in his diary on January 28, "The Americans have done something clever with their tracks. Their Shermans are crossing ground our Churchills struggle with. Must investigate." The Germans also notice. Wehrmacht. Intelligence reports from January 1944 describe modified American tank tracks with extended width as a significant tactical development. One report notes, "Enemy armor demonstrates unexpected mobility in soft terrain, previous calculations of tank trafficability no longer reliable." February 1944. Army ordnance finally catches up with reality. Field reports are too numerous to ignore. The modification isn't a few isolated cases. It's hundreds of tanks, operating successfully, without a single reported failure attributable to the extended connectors. Ordnance dispatches a team of engineers to Italy to investigate. They arrive at 1st Armored Division headquarters, demand to see the unauthorized modifications, prepare to write scathing reports about field fabrication compromising equipment integrity. Then they watch a demonstration. 2 Sherman tanks, one with standard tracks, one with duckbills, attempt to cross the same muddy field. The standard tank bogs down after 30 yards. The modified tank crosses without difficulty. The lead engineer, Captain Robert Walsh, examines a duckbill connector. He measures it. He inspects the weld. He performs basic load calculations. Then he turns to Burke and says, "This shouldn't work. The weld pattern creates stress concentrations. The steel gauge is inadequate for repeated flexing. The attachment point lacks proper reinforcement." "But it does work," Burke replies. "Yes. It works." Walsh pauses. "It works because you're not using it the way we would have designed it. You're using scrap steel, which has already been work-hardened. Your crude welds actually distribute stress better than precision welds would, and you're installing them loosely enough that they flex rather than transferring all stress to the track pin. You've accidentally created a better solution than we would have engineered. That admission changes everything. On February 22, 1944, Army Ordnance officially designates Burke's modification as the Extended End Connector, Type 1, Field Expedient. The designation authorizes production and installation across all theaters of operation. Engineering teams are dispatched to formalize the specifications, but the basic design remains Burke's rough welded footprint. March 1944. Production accelerates. Small machine shops across Italy receive contracts to manufacture duckbills. The modification is so simple that any facility with welding equipment can produce them. By April, production has expanded to England, where workshops gear up to supply Normandy invasion forces. The design evolves. Someone discovers that European workshops have better steel than Burke's original scrap material, so they make the connectors slightly thinner but stronger. Someone else designs a mounting system that lets the connectors be quickly replaced when they wear out. Another innovation, discovered accidentally, shows that reversing a few of the connectors on each track improves traction without compromising flotation. Burke never claims credit. When reporters try to interview him in March 1944, he declines. He tells them to talk to the tank crews. He's just a welder. He made something that needed making. June 6, 1944, D-Day, Normandy, France. 400 Sherman tanks storm the beaches at Omaha and Utah. Approximately 60% have been fitted with extended end connectors manufactured from Burke's original design. The modification proves critical. Normandy's beaches aren't sand. They're sticky clay mixed with seawater, creating conditions almost as difficult as Italian mud. Shermans with standard tracks struggle to climb from the beach to the bluffs. Several bog down in the tidal zone. Shermans with duckbills maintain mobility, cross the beach, and push inland. The difference, measured in minutes, saves lives. Tanks that reach cover quickly survive. Tanks that stop in moving die. Throughout the summer of 1944, as Allied forces grind through the Norman bocage, the extended end connectors become standard equipment. Tank crews request them specifically. Maintenance units install them routinely. What started as an unauthorized field modification becomes indispensable. The British adopt them. The Canadians adopt them. Even the Soviets, receiving American-built Shermans through Lend-Lease, request that the tanks arrive with extended connectors pre-installed. The modification transcends national boundaries because it solves a fundamental problem. Tanks need to move, and narrow tracks limit movement. September 1944. U.S. Army Tank Automotive Command conducts a comprehensive study of Sherman mobility improvements. The report analyzes every modification, upgrade, and field expedient developed during the war. The extended end connector receives special mention. This field-developed modification reduced immobilizations due to soft terrain by approximately 78%. Estimated tactical advantage, the equivalent of adding 200 additional tanks to operational inventory without manufacturing cost. Estimated lives saved, several hundred crew members who would otherwise have been killed or captured in immobilized vehicles. November 1944. The autumn rains turn Europe into a swamp. From Holland to Italy, Allied armour operates in conditions that would have been impossible a year earlier. Extended end connectors make the difference between mobility and paralysis. German defenders, already overwhelmed by Allied numerical superiority, lose their one remaining advantage: terrain. The Panther's superior flotation no longer matters when Shermans can cross the same ground. A German tank commander, captured near Metz in November, tells his interrogators, "We expected the mud to stop them. It always stops them. But this time, they kept coming. Their tanks have new tracks, wider. We did not account for this." The modification appears simple, almost trivial. A piece of steel welded to a connector, 8 minutes to fabricate, 64 per tank. But simplicity doesn't diminish impact. In warfare, mobility is survival. An immobilized tank is a dead tank. A mobile tank can attack, retreat, reposition, survive. The extended end connector, crude and ugly, purchased mobility with scrap steel and welding rod. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. December 1944. Production statistics reveal the scale of adoption. US factories have manufactured over 400,000 extended end connectors. European workshops produce an additional 200,000. Total Sherman tanks equipped, approximately 8,000. The modification has been replicated on other vehicles too. Tank destroyers, self-propelled artillery, even some half-tracks receive modified track extensions. The cost per tank, approximately $47 in steel and labor. The benefit, measurable reduction in combat losses due to immobilization. A post-war analysis conducted in 1946 calculates that extended end connectors prevented an estimated 900 tank immobilizations that would have occurred under standard operating conditions. 900 tanks that stayed in the fight. 4,500 crew members who didn't become casualties while attempting recovery operations. Burke never receives formal recognition beyond the standard campaign medals. No Congressional Medal, no Distinguished Service Cross. His name doesn't appear in history books. When the war ends, he returns to Philadelphia, takes his old job at the naval shipyard, tells nobody about the modification he invented. In 1952, a tank historian researching Sherman variants contacts the Army, requesting information about the origin of extended end and connectors. The Army responds, Field expedient developed in Italy, 1943. Inventor unknown. Widely adopted due to operational necessity. Inventor unknown. That's how innovation happens in war. Someone sees a problem. Someone with hands-on knowledge, not theoretical training, improvises a solution. If it works, others replicate it. If it saves lives, it spreads. Nobody asks permission. Nobody waits for authorization. They just build it. The extended end connector's legacy extends beyond World War II. Post-war tank development incorporates the lessons learned. The M46 Patton, America's first post-war medium tank, uses wider tracks as standard equipment. Ground pressure analysis becomes a primary design consideration. Engineers realize that Burke's crude field modification identified a principle they'd overlooked. Flotation matters as much as armor or firepower. The Soviet T-54, developed in the late 1940s, uses exceptionally wide tracks. The designers explicitly cite combat reports from Lend-Lease Sherman operations as inspiration. Soviet tankers reported that American tanks with modified tracks performed better in mud than standard Soviet designs. That embarrassment drove innovation. The T-54's excellent cross-country mobility stems directly from lessons learned by watching American welders modify Sherman tracks in Italian mud. Modern main battle tanks, from the M1 Abrams to the Leopard 2, use tracks 24 to 30 inches wide. Ground pressure calculations are fundamental to design specifications. No modern tank designer would create a 30-ton vehicle with 16-inch tracks. That mistake has been corrected. Burke's modification, replicated millions of times across thousands of vehicles, taught the world's tank designers a lesson they never forgot. The irony is perfect. German tank designers, celebrated for technical sophistication, created the Panther and Tiger with superior flotation because they understood ground pressure calculations. American tank designers, focused on production efficiency, created the Sherman with narrow tracks that limited mobility. Then, an American welder, with no engineering degree, fixed the problem using scrap steel and common sense. Thomas Burke died in 1976, aged 65, in Philadelphia. His obituary in the Philadelphia Inquirer identified him as a retired naval shipyard worker and World War II veteran. It mentioned no innovations, no modifications, no lives saved. Nobody at his funeral knew that thousands of tank crew members came home because of something he welded in an Italian warehouse in 1943. 3 elderly men attended the funeral who Burke didn't recognize. They approached his widow afterward. One of them said, "We served in 1st Armored. Someone told us he was the welder who made the duckbills. We wanted to say thank you." "For what?" Burke's widow asked. "For keeping our tanks moving, for keeping us alive." She didn't understand. Burke never told her about the modification. He never mentioned Italy. He worked in the shipyard, came home every night, said little about the war. That was Burke. He fixed things. He didn't talk about it. The lesson isn't about technology. It's about initiative. Burke saw a problem that experts declared unsolvable. Official channels said wait for HVSS suspension, wait for proper engineering, wait for authorization, but waiting meant death. So Burke stopped waiting. He picked up scrap steel, fired up a welding torch, and made something that worked. In wartime, that kind of initiative saves more lives than brilliant strategy. Strategy wins campaigns. Innovation wins battles. And sometimes the most important innovation is just a welder who refuses to watch tanks sink into mud while he waits for someone to give him permission to fix them. The United States Army never formally identified Burke as the inventor of extended end connectors. The official record says, "Field expedient, origin unknown." But the men who served in 1st Armored Division knew. The maintenance sergeants knew. The tank crews who crossed muddy fields that should have stopped them, they knew. And maybe that's enough. History remembers generals and battles, but wars are won by sergeants in maintenance depots, making things work with whatever materials they can find, ignoring regulations that prioritize paperwork over survival. Burke didn't need his name in history books. He needed his tankers to come home. The modification gave them a better chance. Today, at the U.S. Army Ordnance Museum at Fort Gregg Adams, Virginia, a display case contains a single extended end connector. The placard reads, "Field Expedient Track Modification, Italy 1943 to 1944, improved Sherman tank mobility in soft terrain, widely adopted across all theaters. Origin. Maintenance personnel, 1st Armored Division. No name, no inventor, just maintenance personnel, but somewhere in that vague designation is a welder who spent 72 hours in December 1943 cutting steel and running welding beads. Who ignored regulations because men were dying? Who created something so simple and effective that it changed how every nation designs tanks? The Germans had better engineering. The Americans had better welders. Sometimes that makes all the difference. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.